I'm Salemi of Device Talks Tuesdays. Welcome to this episode of Device Talks Tuesdays, brought to you by Pulse Technologies. Our topic today is hierarchical surface restructuring for next-generation neural interfacing electrodes and microelectrode arrays. We've got a robust conversation for you. Lots of great slides will be available on the presentation. We will be taking questions at the end. We'll have a Q&A period. We'll try to get to as many questions as we can. If you have your question, please submit it as it comes to you. If we're unable to get to it during the presentation, then the folks at Pulse will get back to you following this presentation. So please get your questions in there. They will have your contact information. They'll be able to get back to you with an answer. So please participate with your questions. And of course, if you are tweeting, please use hashtag DeviceTalksTuesdays. And also, I should remind everyone who's listening, this will be available on demand. So if you know of a colleague or a friend who would benefit from this conversation, please let them know. They can go to DeviceTalks.com to watch the presentation and to ask their own questions. We'll make sure those questions get over to Pulse Technologies as well. So before we begin, I just want to remind you that we have our in-person meeting coming up on October 19th and 20th. That's Device Talks West. So go to DeviceTalks.com for more information about that and more information about our podcasts. All of our podcasts are available on DeviceTalks.com, including Stryker Talks, Intuitive Talks, Device Talks Weekly, and Medtronic Talks. They're also all available on major podcast players. So Amazon, Google, Spotify, you name it, we're out there. So please do check out our podcasts. But we're here today to talk with our friends at Pulse Technologies. Happy to introduce Shahram Amini. He's the Director of R&D at Pulse Technologies. Once again, I'm going to hand the presentation over to him. We'll have some questions and answers, and I know we'll have answers at the end. And then once again, if you have questions, please get them in as soon as possible, and we'll try to get answers for you. All right. With that, I'd like to hand the button over to you, Shahram. Take it away.
Thank you. Can you hear me okay?
Can hear you fine.
Perfect. Thank you, Tom, for the introduction. Ladies and gentlemen, good morning, good afternoon, and good evening to all of you from wherever around the world that you're joining us today. On behalf of my management, all of my colleagues, and all of our collaborators, I would like to thank you all for attending this session today. I do hope that you find the content of this talk useful and worthwhile your time. And all of us at Pulse look forward to working with you in the near future if you think that this technology can benefit you in any shape or form. So I would like to start by a brief overview and introduction. Then we'll move on to the concept of electrodes and electrode arrays and the choice of materials that are commonly used in the manufacturing of electrodes, followed by the existing electrode surface treatment technologies that currently exist. And then I will introduce our patented hierarchical surface restructuring technology, its many benefits, and our recent advances and breakthroughs. I would also be happy to answer any questions, as Tom mentioned. Please send them through, and I'll try to answer as many of them as time permits. So aging population and existence of a multitude of cardiac, neurological, retinal, and hearing disorders that cannot be cured solely by medication have all kind of resulted in a significant growth in the number of patients that require long-term implantable and diagnostic devices. These devices and their application examples range from say, cardiac rhythm management and electrophysiology, cardiac mapping devices for treatment and diagnosis of cardiac disorders, neurostimulation devices for deep brain, spinal cord, sacral nerve, or vagus nerve stimulation for treatment of a really large suite of neurological disorders, such as Parkinson's disease and tremor, to suppress and treat, for example, epileptic seizures, and for epilepsy diagnostics, for brain-computer interface and recording of electrical signals from the surface of the brain, pain management, overactive bladder, and urinary retention disorders, and so on. And also retinal prosthesis and bionic vision for vision restoration, and last but not least, cochlear implants to treat hearing disorders. So simplistically, if we want to describe the functions of these devices function through the application of artificial stimulation to living tissue through transfer of an electrical or external electrical signal from an implantable pulse generator or IPG to an implantable electrode or an electrode array, and then across to the membrane of the neural cells or tissue for the intended purpose of this or any specific device. The signals in the body traveling from the brain to the muscles are electrical. The signals also going from the sensory organs to the brain are also electrical signals. And the nervous system in the body basically transports these signals. So if a nerve is injured and the communication between the brain and the periphery is somehow disrupted, for instance, in the case of spinal cord injury, it is possible to use a device to either record this information from the nervous system or to restore the function that the brain cannot control. So majority of these devices consist of essentially three major components. The IPG, which is the implantable pulse generator, or in some cases referred to as neurostimulator, that contains battery and electronics and the circuitry of the device, which essentially is the brain or the CPU of the device. Electrodes or microelectrode arrays that are responsible for sensing and recording of neurological or cardiac activity, and leads that basically bridge between the pulse generator and the electrodes or microelectrode arrays. Some examples are shown here on the slides. For example, example of a responsive neurostimulation device, which is implanted in the skull, replacing a similarly shaped section of the bone, and also the cortical strip and the depth electrodes that are platinum iridium alloys that are implanted in or on the epileptic seizure focus. Another example is the cochlear implant electrode array with 22 electrodes made out of platinum iridium, and with increased number of electrodes of essentially smaller geometric surface area, stimulation of more discrete groups of auditory neurons is enabled that can improve speech perception in patients who are profoundly deaf. So another group of examples that I'd like to show you is, basically in the cardiac world, cardiac pacing world, essentially advances in cardiac surgery towards the mid-20th century created a need for artificial means of stimulating the heart muscle. And initially, devices were developed as large external devices, but with improvements and technological advances that resulted in miniaturization of electronic circuitry, and eventually the development of totally implantable devices led to basically devices that we see today, like the cardiac pacemakers and defibrillators that are in the market. CRM devices generally treat and manage basically cardiac-related diseases for either too slow of a heart rhythm, for example, through implantation of a pacemaker, or too fast of a heart rhythm, for example, through implantation of defibrillators. So there were multiple paradigms in the cardiac pacing market, and it started with external alternating AC-powered devices, and that evolved to wearable kind of battery-powered pacemakers, and that led to the paradigm of basically fully implantable pacemakers that you see many examples of them today. and basically the emerging and rapidly developing new paradigm of leadless pacemakers was next, which actually is here now because leadless pacemakers are implanted in human body and are in clinical use. But now that I've provided a brief overview of the various sorts of neural interfacing devices and the way they function, we can shift gears a little bit and talk about the materials that are in the fabrication of electrodes and electrode arrays for these devices. Generally speaking, there is currently two materials commonly in practice. First one is a platinum iridium alloy, which is the most commonly used alloy due to its unique chemical, electrochemical, and mechanical properties. It is used in the manufacturing of leads and electrodes in neurostimulation devices, cardiac devices, and also cochlear implants. The second material is, less commonly used, is titanium, but on the other hand, is very, very critical, is very strategic, and I will explain why. It is primarily used in the construction of the leadless pacemaker can or the container because titanium is obviously much lower cost, much cheaper compared to platinum and precious metals, is biocompatible, is chemically resistant, corrosion resistant, but due to the formation of an inherent titanium dioxide layer that is extremely thin on its surface, which is also not conductive, is electrochemically very, very poor compared to, for example, platinum iridium alloy. Therefore, there is a need to make titanium electrochemically active, particularly for these leadless applications. As you can see, since titanium has limited applications, I pose a very important question here that could there be other applications for titanium, or could there potentially be other applications for titanium as an electrode material if it could exhibit exceptional performance? This is a very important question and a game changer. Sorry, my slides are flipping a little bit. So this is a very important question and a game changer for this industry, and I hope by the end of the presentation you will have the answer. We talk about electrochemical performance. It's really important to understand what I mean by that. There are several in vitro and in vivo methods of electrode characterization that are relatively well established. These are two common in vitro techniques for electrode characterization. Number one is cyclic voltammetry, that essentially identifies the presence of electrochemical reactions and provides information on the reversibility of reactions, and is valuable for assessing stimulation capacity and efficacy, and also the electrochemical impedance spectroscopy, which is a valuable assessment or measurement technique for recording capabilities of electrodes that measures essentially impedance at the electrode and at the interface of the electrode and the biological environment. So in our work, in order to assess the EC performance of our electrodes for comparison's sake, we both use CV and EIS measurements. I believe somebody from DeviceTalks, if you may mute your microphone, I would really appreciate. There's a lot of background noise. I appreciate that. So we use essentially CV and EIS measurements in a 3-electrode cell comprising a silver chloride reference electrode, a platinum canal electrode, using commercially available phosphate buffered saline or PBS solution. And going forward, basically the results that I will show talk about these two measurements and the comparison of electrodes using these two measurements. So let's look at platinum iridium, as we talked about, and titanium as a starter. So these two metals, without any surface treatment or coating or any addition to the surface, are generally poor materials electrochemically. Platinum iridium is electrochemically more active and better than titanium. From the CV and EIS plots that I'm showing here, you can see that platinum iridium charge storage capacity total is around 1.5 millicoulombs per centimeter squared, and its specific capacitance is around 0.6. And those same parameters or performance matrix for titanium are around 0.2 and 0.17 on average, and that's why titanium is much poorer compared to platinum iridium. So another question that I'm posing here is that, is there another surface treatment technology that is more advantageous and commercially viable in order to enhance the electrochemical activity of the electrodes in the body? And I hope that I will be able to answer this question by the end of the presentation. So when you look at the older generations of, for example, percutaneous and paddle lead and paddle arrays, they typically included 4 electrodes, for example, but with larger geometric surface area. And however, as device manufacturers are shifting towards devices with improved simulation efficacy, selectivity and also flexibility, the newer generations of electrode arrays are made with much larger number of electrodes, oftentimes up to 8, 16, and even 32. But because of the limited space in the body, such as brain or spine, once the number of electrodes is increased for efficacy and selectivity, then the geometric surface area of the electrodes should decrease, but reducing the size of the electrodes actually leads to lower electrochemical performance. So essentially, larger electrodes, as I said, have greater geometric surface area and therefore can inject more charge before they exceed the electrochemically safe limits in the body. However, their large size limits the spatial selectivity and resolution of the device. As I said, in order to increase the charge injection capacity for delivering a higher resolution signal and also improving performance, we can increase the geometric surface area by increasing the number of electrodes. But nevertheless, considering the space limitations, as I said, such increase in the number of electrodes must be accompanied by a reduction in the electrode size, which significantly reduces the amount of charge that can be delivered, and also it increases the impedance of the electrode. Therefore, this adversely impacts the device performance and defeats the purpose of increasing the number of electrodes. To overcome this trade-off, an alternative approach is to increase the number of electrodes to achieve high selectivity or, for example, flexibility in the device, where each electrode has a smaller geometric surface area, but with enhanced electrochemical surface area, and that can be achieved by technologies such as coatings and certain surface treatment technologies that could be applied on the surface. So in summary, in order to reduce the geometric surface area of the electrodes, more and more materials, coatings, or surface technologies that have more and more electrochemical performance are needed, and that's really the essence of what I'd like to talk about today. But there's always a limit, and the limit is, by how much you could actually improve the surface by adding either a surface treatment or a coating or an additive material onto the surface to create basically to make an electrode that is electrochemically active. And those limits are really kind of the stumbling blocks. And what I'd like to do, I'd like to come back to this and revisit this as to how we have actually overcome this limitation. So there are a large number of techniques, materials, and solutions out there that currently are used for electrodes. Platinum black, has been used in a number of for a number of years and is still being pursued. It has it is essentially a nanoporous platinum coating that has very high surface area and, as a result, high electrochemical performance, but it has very low and poor durability. Titanium nitride has been widely used. It is a chemically stable metallic conductor with excellent biocompatibility and excellent electrochemical performance, and has been used widely for many cardiac rhythm management devices. Iridium, when it is sputtered in an oxygen-rich environment, has been shown to result in iridium oxide coatings that oxidize and reduce, can oxidize and reduce in a reversible way in order to enhance charge exchange for neurostimulation applications. Other platinum group metal oxides, such as rhodium oxide, palladium oxide, and ruthenium oxide, have also recently shown to exhibit some desirable level of electrochemical performance, but without much clinical evidence. It has also been shown that solid solutioning of platinum and platinum group metals can improve their performance. Other techniques such as electrochemical roughening, and conductive polymers and carbon-based coatings have been used extensively in order to improve electrochemical performance of electrodes. And last but not least, laser-based techniques such as laser melting and laser etching have been studied and basically investigated in some length, but studies have been kind of on an ad hoc basis, and there hasn't been really any systematic work to essentially explore their applicability in medical device applications in this space. But let's kind of summarize quickly the disadvantages and shortcomings of existing surface technologies: limited performance, durability, scalability, and throughput, costly and time-consuming vacuum and batch processes when, for example, coating techniques are used, poor adhesion and susceptibility to delamination, cracking, and spallation of the coating. Most coatings is an issue. Costly precious metal requirements for coatings. Most coatings, whether it's a platinum iridium thin film or iridium oxide, there are requirements for basically expensive precious metal targets. Masking challenges in most coating techniques for complex electrodes where certain portions of the device or the electrode needs to be masked is an issue, and time-consuming and costly, and poor long-term durability and performance are amongst some of the disadvantages of existing technologies that are basically out there. But what is the solution? What is it that we're offering? What is hierarchical surface restructuring? Hierarchically structured surfaces essentially exhibit topographic features that are comprised of varying length scales that are, core scale structures, several microns in size, to a range of about 10 to about 100 microns, and a finer structure subset on top of the core structures in the range of a few nanometers to a few hundred nanometers in size. And you could see some examples of basically scanning electron microscope images of these hierarchical structures that have been produced on the surface of electrodes. Over the last several years, we have developed the applicability and performance benefits of femtosecond laser hierarchical surface restructuring technology. We have explored the tunability of performance as a function of several readily accessible laser parameters on a wide array of electrode materials and geometries for a large number of devices and applications. As an example, on the top right section of the slide, you can see the hierarchical surface structure that is induced on the surface of a platinum 10% iridium alloy electrode that is used for a paddle lead spinal cord stimulation electrode array. So our patented technology has numerous benefits compared to other existing surface technologies for electrode surface modification. It creates a hierarchical surface structure that essentially leads to ultra-high surface area. It can be used on complex geometries, complex electrodes. The tunability of performance and the tunability of the surface topography and the surface structure of the electrode is really, really an important attribute of the technology, because you could essentially tune the performance the way you like. Obviously, with every process, there are limitations and some limits as to how far you could actually drive performance and how far you could tune, but the process has extremely ability to be tuned, both performance-wise, electrochemical performance, as well as surface and topography of the surface of the electrode. Unlike other techniques, there are no coating overspray, there are no adhesion failures, there are no batch minimums. You could restructure one electrode, you could restructure thousands of electrodes. So there is no batch minimum. It's a maskless process. It reduces the cost of masking compared to other techniques such as coating. It's applicable on various materials. As I mentioned, for example, we could work with platinum-based electrodes. We could work with titanium and titanium alloys and other materials such as stainless steel, tantalum, and other metallic electrodes that we have worked with. And also it's applicable on many different geometries and shapes, such as foils, sheets, tubes, and etc. So that's really a very interesting attribute of the process of this technology. So here I'm showing some examples of real-world electrodes that have been restructured using our patented HSR technology. From top left, you will see a cylindrical platinum iridium electrode for cardiac pacing applications. Then next to that, you see a helix platinum electrode, again for cardiac applications, a helical electrode, a rivet-style platinum iridium electrode for an electrophysiology mapping catheter. Then next to that is a cylindrical platinum iridium electrode for use in a percutaneous spinal cord stimulation electrode array. And then to the very right is a flat electrode that is used in a paddle lead spinal cord stimulation electrode array. All of these are examples of real-world devices that we've worked with many customers and developed for them. I talked about tunability. As mentioned earlier, our technology has introduced a novel method for hierarchical surface restructuring of electrode surfaces using femtosecond laser, and the process promotes tunability and controllability of the electrochemical performance and characteristics of electrodes for various neural interfacing applications. There are a number of ways that we could actually tune and engineer the surface of the electrode in order to create topographies and surface structures that vary from one to another, and that way we could actually tune and engineer and design the kind of performance that you are interested in your devices, and that's really incredibly unique in our opinion. So whether by adjusting and varying laser specific parameters such as laser power, average power, fluence, energy per pulse, repetition rate or frequency, beam size, spot size, or by varying lasering patterns on the surface, we have really an enormous number of ways in our toolbox to be able to tune the surface and control the electrochemical performance of the electrodes, which again makes the process very, very unique. And as you can see, a wide range of electrochemical performance matrix, such as charge storage capacity, specific capacitance, and impedance, are achievable with this process and the way it could actually tune the electrode surface and the electrode electrochemical performance. If you remember from earlier, I mentioned that the emerging and rapidly developing new paradigm and the era of leadless pacemakers started several years ago. But why is this paradigm important? It is important because it essentially redefined an almost a 90-year-old industry, and that redefinition then brought with itself new requirements and the need for a redefining surface treatment technology for cardiac pacing applications, because leadless pacemakers are fundamentally different than traditional pacemakers with leads. And that has been the driving force behind our efforts developing a surface solution that can address the needs of this very particular market. So I'm really proud to say that we've developed a proprietary process that can hierarchically restructure high-performing titanium electrodes as a low-cost alternative to platinum-based electrodes. The technology offers numerous benefits over titanium nitride coatings that are traditionally used in CRM or cardiac rhythm applications as a coating on platinum-based electrodes. The technology has essentially redefined the CRM electrode technology because it offers many, many benefits. For example, in situ synthesis of high surface area titanium nitride, the low cost of the process, because it actually doesn't require the use of costly platinum iridium electrodes, but instead uses titanium. And unlike PVD-based titanium nitride coatings, it is a maskless process with no batch minimums, as I mentioned. And it creates electrochemically active ultra-high surface area due to the presence of nanostructured titanium nitride that is actually synthesized in situ during the restructuring process. And last but not least, again, the surface tunability and high electrochemical performance makes it really, really ideal for use in not only cardiac rhythm management devices and in leadless pacemakers, but in many other neural interfacing applications. And in fact, we are working with a number of customers who are benefiting from the use of titanium, and they're thrifting from basically use of platinum and platinum-based electrodes in their devices because of this ability that we have to restructure titanium. And I mentioned tunability. I kind of show it here microstructurally. Tunability can be achieved by varying a suite of lasering and basically lasering parameters that can in turn create a large array of morphologies on the surface of titanium electrodes similar to platinum iridium. And going from top left to right and then down from bottom right to the left, you could see that how more and more aggressively electrodes could be restructured in order to exhibit larger and larger electrochemical performance depending on the need of the device and depending on what level of electrochemical performance is desired in your device. So I touched upon this briefly earlier, but one of the benefits of this technology is that it is essentially kind of geometry agnostic. So you can clearly see examples of cylindrical, helical, and flat electrodes that we have successfully restructured for a number of applications. We've worked with sheets, foils, extremely thin foils for a large number of applications. So it really is, I guess the best way to put it is a geometry agnostic process and can work with many, many different complex geometries surfaces, electrodes, and materials, which is truly unique. One of the concerns for some device manufacturers has always been whether or not electrodes that are already assembled on a lead can be restructured in situ. And the answer is yes, generally yes, it can be done. There are, of course, complications with assembled leads, as there is a great degree of care that needs to go into handling and fixturing and selection of the laser parameters to successfully restructure the electrodes on the lead without actually damaging them. You can see an example of a percutaneous lead with 8 cylindrical electrodes. The image shows only 4 electrodes that has been successfully restructured without any damage to the lead. So to answer, those who are interested in restructuring assembled leads, yes, it can be done, but again, it all depends on the needs and obviously the type of array, the type of lead that we're working with. One of the other benefits of the technology is that it can be applied on electrodes with existing surface texture or mechanically induced textures. Here you can see examples of a neurostimulation device electrode that was mechanically stamped in order to create dimples on the surface, which was subsequently restructured using our HSR technology successfully, and you could see that really the degree and the uniformity of restructuring is pretty remarkable on an electrode that is already mechanically textured. So that's kind of an interesting aspect of the technology as well. So one of the things that we have developed over the last year or so is basically the use of our HSR technology with Tandem gas injection system technology. It's very interesting because it uses a synchronized communication between a lasering system and a gas injection system for HSR processing using a proprietary tracking algorithm. It has a number of advantages and benefits. For example, high quality, treated surfaces, complete elimination of redeposition during basically restructuring treatment, and significant reduction in heat-affected zones. So many electrodes, if you're interested in kind of an aggressive level of restructuring, they require basically an aggressive level of restructuring. Therefore, heat-affected zones could be a challenge. So this gas injection, tandem gas injection system and technology can eliminate that, and also has a benefit of reducing the processing time of restructuring, and it also allows us to have access to a larger array of kind of fluences and laser energies that can give us the ability to basically restructure more aggressively. And more aggressive restructuring is equal to basically more and more gain in performance. And also tunability for new applications and different electrodes and geometries is really something that can be leveraged using this new capability that we have developed. As an example, you could see the difference between electrodes that are restructured with a gas injection system and without. And so there are, again, a number of benefits doing this. For example, we've seen and received feedback from some customers that there is some dissolution of the electrode in certain cases under extreme pulsing conditions, and we've been able to basically work with this tandem gas injection system technology in order to kind of reduce the amount of redeposition and recast on the surface of the electrode after restructuring, which makes it kind of really interesting and unique in many ways. So many of our customers also require additional features to be created on their electrodes. These features could be holes or trenches, for example, or some customers require the electrodes to be laser cut after restructuring. So that's also really important. So the Tandem gas injection system technology is really an excellent enabler here for these applications. Drilling and machining holes with large aspect ratios without any heat-affected zones, and kind of elimination of redeposition and recast to create smooth surfaces are amongst basically some of the benefits of this technology that we've developed. Clearly on the bottom you see the same process applied with the gas injection, and on the top row you could see same lasering parameters but without the use of the gas injection, and the differences are very clear and obvious. So we've had this question asked from us a number of times regarding the biocompatibility and whether or not after surface restructuring the electrodes are biocompatible or not. We've conducted a series of biocompatibility studies under ISO 10993, including cytotoxicity, skin sensitization, and irritation. And all the results of these tests have indicated that the HSR treatment does not elicit a cytotox effect, nor any sensitization or irritation, which is obviously great news. With regards to clinical evidence, it would be a remiss if I didn't talk about our clinical evidence and commercial success with a device in which our HSR treatment and HSR technology has been utilized and approved by the FDA. Cardiac pulmonary nerve stimulation is an innovative new treatment that is under investigation for patients suffering from acute decompensated heart failure, ADHF. It is designed to increase contractility of the heart to pump more blood to the rest of the body. Our proprietary HSR technology has been utilized as part of Cardionomics' cardiac pulmonary nerve stimulation system for treating patients suffering from ADHF. And it has truly been an enabling technology for Cardionomic and for their new device, and all of us at Pulse are truly excited for this new development. So remember the question I posed earlier: is there another surface treatment technology that is more advantageous and commercially viable in order to enhance the electrochemical activity of the electrodes in the body? So I thought that was an important question that I raised. And so the answer is absolutely yes. Our patented HSR technology is really unique in a number of ways. It's a unique technology targeted for next generation neural interfacing electrodes and electrode arrays, due to the many benefits that I outlined and I talked about throughout the presentation. The ability and the way that the process can tune the surface in order to achieve a large, really large range of electrochemical performance is really unique. And when you compare that with many existing materials out there, such as iridium oxide, titanium nitride, platinum-based coatings, PDOTs, and other techniques that have been studied, it shows an unprecedented level of performance increase, and it allows us to really take electrodes and electrode arrays to the next level in order to design and build devices with our customers that are really meant to improve patients' lives and to make devices that are unique in so many ways. So with that, let me wrap up by some concluding remarks. Our HSR technology offers numerous benefits and advantages over existing and conventional surface treatments and surface technologies that are out there. The hierarchical surface structure induced on the surface that leads to ultra-high surface area and unprecedented electrochemically active surface area is really unique. The surface and performance tunability, no coating overspray, no adhesion failures, no batch minimums, maskless process, and the applicability of the process on various materials and alloys and metallic electrodes, and its applicability on foils, sheets, tubes, and complex geometries for a large number of applications, and its suitability for use in a really large range of neural interfacing applications, and the fact that it is scalable and commercially viable and is also cost competitive compared to coating technologies is really has really put this technology ahead and above of many other surface treatment technologies that currently exist out in the market. Many people have contributed to the research and the work that I presented here. These are outstanding engineers and staff at Pulse Technologies, and some very, very talented students, professors, research scientists, and postdocs from several universities with whom we have been collaborating on our research and development efforts over the last few years. Without these excellent people, both at Pulse and externally, these developments would not have been possible. And with that, I would like to conclude the presentation and pass the podium to Tom. Again, on behalf of all of us at Pulse, I would like to thank you for your time and attention today, and I look forward to answering as many questions as time allows. Thank you.
Excellent, great job, Sharam. Thank you for that presentation. It clearly a very robust offering of information and insight. So, and we have an abundance of questions here. We'll begin to work through them, but it's very likely that that Pulse will be getting back to some of you directly. Do not let that stop you from asking a question as we go forward. If something is already top of mind, or if the questions I'm about to ask generate more questions, feel free to ask away. And once again, we'll pass all the information on to Pulse, and they'll be able to get in touch with you. So looking at the questions, someone asked, you talked about restructuring of titanium and then presence of titanium nitride on the surface. How does it work? Can you describe it?
Sure. Great question. So the restructuring of titanium, as I mentioned, titanium itself, as I mentioned, is electrochemically poor because of the formation of titanium dioxide on the surface, an extremely thin layer of titanium dioxide, which unfortunately is non-conductive, and it renders titanium electrochemically poor. Therefore, we need to promote formation of something that is electrochemically active, and that something would be titanium nitride, because essentially we could perform the restructuring of titanium in a controlled environment with nitrogen. So essentially the process is done under nitrogen, and that promotes synthesis and formation of titanium nitride on the surface. And basically the formation of titanium nitride in tandem with the increased surface area on the surface of the electrode as a result of laser restructuring both contribute significantly towards improvement of electrochemical performance of titanium electrodes after restructuring. So essentially, we turn a very poor electrochemical, a very electrochemically poor material, such as titanium, to an increasingly, a very exceedingly electrochemically active electrode material when we restructure that under a nitrogen blanket in a nitrogen-rich environment.
Great. All right, our next question is, let's see, what are the limitations in terms of geometry of electrodes that can be restructured? For example, is there any limitation about thickness?
It's a great question. With every process, there are some limitations, but as I mentioned, our process is kind of geometry agnostic. It as long as the laser beam can reach the surface, it can be restructured. So I showed some examples of very, very complex geometries, such as a helix, or, for example, a cylindrical electrode, and some curved surfaces. So I can think of a situation where we have been asked to restructure an electrode with a complex geometry where we haven't been able to do it. There are, however, limitations in terms of thickness. So thickness of the electrode is really, really important, because the process essentially is using laser, and the laser spends a good amount of time on the surface of the electrode in order to restructure that surface. And there is also inherently some degree of material ablation from that surface. And in fact, perhaps I could see if I can bring one of the slides that could hopefully. Can you see this slide now?
Yes.
Okay, perfect. So that's on the top left. Let me see if I can bring my laser pointer. So right there, that confocal image that I'm showing, it shows the unrestructured surface of an electrode, which is kind of the gray area, the white grayish area, and then it shows the restructured area. So you could see that there is some degree of material removal or ablation in the order of a few microns from the surface. Therefore, if the electrode is extremely thin, there might be some limitations. And so always, that's one of the major questions and the biggest question that we always ask our customers: what is the performance level that you're interested in, and what is the thickness of your electrode? Because if you're interested in an extremely high degree of electrochemical performance and your electrode is extremely thin, then unfortunately, it's not practical. But we have been able to work with a number of geometries and thicknesses, and very successfully. So if you have a need, please reach out. We'd be happy to talk to you.
So what's been the thinnest electrode you've successfully restructured, and what's it used for? What were the applications?
I'm sorry, you said, can you repeat the question one more time, please? Sure.
What has been the thinnest electrode you've successfully restructured, and what were the applications?
Sure. The thinnest electrode that we've been able to work with successfully has been a very thin foil of platinum iridium used for a deep brain stimulation application, and the thickness of that was 1 thou, 25 microns. That has been restructured very successfully, has had I don't recall. I don't want to mention a number that is incorrect off the top of my head, but significantly we were able to increase the electrochemical performance of the foil electrodes, but obviously not to the extent where, for example, we could work with a percutaneous or cylindrical electrode, where the thickness is oftentimes 4 or 5 times than a thin foil that is used for deep brain stimulation application.
Right. And we'll keep going through these. Someone's asking, what drives the cost of this technology? And the follow-ups are, is it the number of electrodes or is it performance-based?
It's both and more. So obviously, the number of electrodes, the quantity of electrodes that somebody is interested in restructuring, performance is a huge factor, because the higher the performance, the longer the laser needs to spend time on that surface and do its magic. Therefore, laser time equals cost. So if there is no need to achieve, let's say, a charge storage capacity of 300 millicoulombs per centimeter squared, don't do that, because it simply adds cost, and you don't need that. So essentially, performance and laser time are kind of hand in hand, directly proportional, and those together basically drive cost. And we talk about, obviously, number and quantity. That is surface area. So the larger the surface area of your electrode, or the total surface area of a lot of electrodes that require to be restructured, basically define and drive the cost of this technology and the process.
And we'll try to work through these quickly. Someone's asking, are there any general design considerations that should be made for restructuring?
They're really, I would say, for us, it's important to understand, the end use. So as long as we understand the end use and whether or not there are any performance matrix or targets that you have in mind to achieve, it helps us a lot. And then we can make recommendations. With the understanding of basically the performance requirements and the end use, hopefully we can design a process, we can design a method, and work with you in order to efficiently and effectively restructure electrodes that meet your requirements.
Okay. And we have a question here about the tandem gas injection technology that says, you talked about the tandem gas injection technology you've developed. How does it work? What kind of gases are you using in this process?
That's a great question. Generally, the gases are gases that have the ability to basically generate cooling, and also gases that have the ability to basically remove material during restructuring from the surface. CO2 is an example. Supercritical CO2, in its solid liquid, gas state, can actually does a lot of really cool, interesting things. It could, on impact, the solid snowflake type particles of CO2 could essentially remove material, and the gas and the liquid phase could potentially cool the surface of the electrode, and that opens up really a lot of avenues for us in order to explore restructuring of newer devices and more delicate devices, and maybe thinner electrodes and things of that nature.
And we're up against the clock, but final quick question. I see one here. Someone's asking if you're able to work on prototype samples. And before I let you answer, we let folks know there are a lot more questions here. We do see them, but unfortunately, we'll need to get back to you. Pulse will get back to you directly after the presentation. So, last question: are you able to work on prototype samples?
Absolutely. We're here to help. We're here to do exactly as you asked. We would love to work with you to provide you with prototypes. If you have specific electrodes and specific needs in mind, please reach out to us. Generally speaking, we tend to turn around very quickly on prototypes. We always have a large number of projects, and we would be happy to work with you and get back to you as quickly as we can. Fantastic.
Great. Shahram Amini, thank you for your time and insights today. Been a great presentation. Lots of fantastic information. And of course, thank you to our attendees. A lot of great questions here. We did not get to many of them, which is a sign of a good presentation. But Pulse Technologies will connect with you following the presentation. I'm sorry we couldn't get to your questions during the presentation, but we do thank you for joining us today on Device Talks Tuesdays, and hope you'll turn into a future episode. Have a great night or afternoon.
Thank you.